So let's start. Hi, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thanks for joining today. Our seminar is generously sponsored by 2 Sigma. It's my real pleasure to introduce our distinguished speaker, Professor Alex Shapiro from Georgia Tech. Professor Shapiro is Russell Chandler III Chair and Professor in the School of Industrial and Systems Engineering at Georgia Tech. He has made many fundamental contributions to the field of mathematical optimization, and he has published more than 140 research articles in peer-reviewed journals and is a co-author of several books as well. He was on the editorial board of several prestigious journals, and he was an area editor of optimizations and he was an area editor of operations research, and the editor-in-chief of the mathematical programming series A. In addition, in 2013, he was a recipient of the Kachian Prize awarded by the Informs Optimization Society, and in 2018, he was a recipient of the Danzig Prize awarded by the Mathematical Optimization Society and Society for Industrial and Applied Statistics. Early in February this year, Professor Shapiro was elected to the National Academy of Engineering. We sincerely congratulate him on this extremely prestigious honor. Today, Professor Shapiro is going to talk about recent advances in stochastic programming. Please join me in welcoming him.
Thank you very much for this nice introduction and for inviting me. So, let me start with few general remarks. Traditionally, there are several groups, research areas, which were supposed to deal with uncertainty and especially optimization under uncertainty. Everybody probably knows this Markov decision process, optimal control, and stochastic programming. So historically, stochastic programming, going back, origins of stochastic programming can be traced back to early days of linear programming, especially with 2-stage. And for many years, the development in stochastic programming was basically very much independent from these areas of say, MDP or optimal control. And so also the class of problems which were supposed to solve by all this in these areas were a lot of overlapping and somewhat similar in many ways. The modeling approaches, computational approach, theoretical developments were quite very different in stochastic programming. I will try today to give a certain type of view of this type of optimization from the point of view of stochastic programming, and probably I'll mention that what is our recent developments of that. Let me also say what I say today is my personal opinion. Maybe not everybody will agree with me, so please excuse me for that. So I'll try to give just a general overview of how I see it. Okay, so when we make the decisions, we have typically, and this is from statistical point of view, I teach statistics classes and all that, there's data, we have supposed to date, we observe something, right? So we have some process. How we model this process can be very involved. So when we make decisions, usually this, especially when we look at the multi-stage, we can make the decision when we observe something, some realization of data. I didn't say it purposely, I didn't say random, because there's a different way how uncertainty can be modeled. Then we make decision, observe something, and go on. Now, here we assume that we have some uncertain process, and you see the indexes can be written in a different way, and our decision at the first stage is made before we make any observation of uncertain data. We make two basic assumptions now, which is, could be somewhat different from what usually people do. And I'll mention it. First of all, we assume that the data process, we model it, is a random or stochastic process. This is a very big assumption. Then we can involve all this probability theory was developed for centuries. Right? So there are many questions about that, and I don't have time to, it's because when we model something, we have to think how we solve it, and so on, and so on, and so on. I'll mention something as I will go on. Second assumption that we'll make, that the probability distribution of this random process does not depend on our action, on our decisions, which is already different from, say, MDP. Why? I'll try to explain it later. Okay? So these are two basic assumptions that I'll make now. Now, so what it means that we make decision. I didn't say anything yet about optimality. We make decisions based on what we observed at every period of time. So at every period of time, t, or stage, we observe the realization of our random process. This is just notation. This is a history of random process. We are supposed to know the past, and keeping record of that, and our decisions are functions of that. We make decisions based on what we observe. This is very important point. Next, we have to define what we optimize. So when we go, in a moment go back, our decisions themselves are random because they functions of a random or stochastic process. This is important to remember. Now, first stage decision is deterministic. It's made before observed any realization of the random data. So next, what do we optimize? In a classical way, we have cost functions which depend on our decision on x and this realization of this random variable. Yes, and one possible way, we look at the total cost. We fix number of the periods, number of stages we look ahead. I'll say some later, I'll say a lot about that. Right? And we take expected value. Please remember this notation that actually xt in itself is random because it's again, it's a function of this realization of the process. This is emphasized here. And we have some constraints which should be satisfied, say, with probability of 1 for almost every realization of the random process. So if I make this decision, if I go back and make decision, how I make the decision at every period of time, I assign to that a policy. It's called decision rule, policy, and so on. So in this formulation, remember, this is deterministic. This is how we set the modeling. This, in that case, we try to minimize the total cost on average, take an expected value. By writing its expected value here, I assume that this has a certain distribution of this process. Even if I don't know the distribution, I assume that it exists somewhere, otherwise I cannot formulate this expected value. Now, sometimes they use this terrible word non-anticipative, that meaning that we make, every time we make decision based on we know at this time, and we don't know what happens in the future. We don't know every period of time. We know, we observe the process. We don't know what will happen, but we assume probability distribution of the future. And this is conditional, because this is how we do that. Now, the most important case is linear, because for many reasons. Because linear, it's going back to all the origins of modern optimization. It very often can be modeled as linear, and it seems to be the most convenient for numerical solutions. So this is a particular case that we will talk about now. So here we have these linear constraints. Typically, it's sometimes balance equations which connect this at a period t or stage t and the previous period, and we minimize the expected value. Again, we optimize that over policies. Now, this is very nice, but every time we model something, on one hand, when we model something, we are supposed to think about that it should be reasonably realistic, close to reality. And on the other hand, we should think how we can, if we can solve that. Of course, even linear, to solve that in a closed form, it's only very, very simple cases. So today we think about that, how can we really solve that numerically? And remember that when we think about solve that numerically, we're supposed to give to the user these functions. So in generally, when I write problem like this, it's infinite dimensional problem, especially if the distribution of this is continuous. And from modeling point of view, for example, when I teach time series or something like that, in modeling, we have continuous distributions. Quite rarely when we have explicitly only discrete distribution, we find a number of possible realizations. So because of that, the problem that formulated that, even if it is linear, is infinite dimensional problem. I cannot put infinite dimensional in a computer. At a certain point, that way or another, one has to make discretization of that. And this is a very big question. Okay? Should be discretized in order to even to write it in somehow in a computer and trying to solve this problem numerically. And what does it mean? We'll talk about it in two stages. Can you hear me now?
Currently, we can hear you.
It was disconnected for some reason for the moment. Okay.
Mm-hmm.
So let me repeat it again. So the way this is written, especially when we model this random process with continuous distribution, which is from application point of view is natural. Nature has infinite number of possibilities. This is infinite dimensional problem, optimization problem. Solving infinite dimensional problems are very difficult. In fact, we have to discretize them. So let us look at the case with just two stages. In a sense, it's the simplest possible. And in that case, we have just one random vector of, say, of dimension d, and we make discretization of that. In a stochastic problem, they call it scenarios. We generate that. If I generate that and we assign to that some numbers, which we call probabilities, then we can write in linear case, we can write that as one large linear programming problem. In other words, we make one copy of the second stage, which is supposed to be a function of this random vector. We have, remember, we have finite number of possible realizations. We make one copy of that. And then we can write whole problem linear. Remember, we'll talk just linear, the simplest possible case, one linear programming problem. The size of this problem is more or less proportional to the number of scenarios which we generate. Assign to that some numbers which we call probabilities. And this is corresponding realization of all these parameters that we have here. Now, the natural question to us, which was ignored for a long time actually, is what do we solve really here? Can we really solve that? Remember, when we look at here, this is the first stage. Usually this is only of interest. After data is coming in, one can recompute it. So how many scenarios I need to generate here to construct possible realization around that I can, when I solve that, it will give reasonable approximation of the so-called true problem. By true, I mean that from modeling point of view, the distribution of my random vector, this number of random parameters, is continuous distribution. Whatever I model. Now, here we immediately see very big problem, computational problem. This is my random vector. This is how many random parameters I have. Suppose D, I have D of them. And the simplest possible case, we assume these are components of that, these are random variables. They independent of each other. These components of this random vector, we suppose we are independent of each other. And each one has marginal distribution. We start to discretize that. Suppose we use just m point, 10 points. It's not that much if we try to discretize continuous distribution. The total number of scenarios here will be m in the power d. So what happens here, that as we enter in the computer our discretization, right, it grows more or less linearly if we fix m, say 100. It grows linearly with respect to dimension d. This is how many discrete scenarios I need, how many discretization I need. But number of scenarios grow exponentially. So it should be not surprising because of that is that from deterministic point of view, trying to solve the deterministic, it's called deterministic equivalent of that, is not computationally feasible very quickly with growth at dimension d. And indeed, the first paper of that time was this paper by that. Later, this was found some inconsistency in this paper. And this very nice recent paper, where it was shown that if we try to solve even a very simple, relatively simple problem with higher accuracy, it's not possible. It's even worse than big height. So from this, in fact, when I remember that this study especially gave talks about that and stuff, it simply was ignored. No, okay, somebody says that you cannot solve. Who cares? Now, what happened until probably 20 years ago, 20, 15 years ago, in stochastic programming, the whole thing was dominated by generated scenarios. Right? What does it mean? Again, one generates certain possible realization of the random process and try to solve what is called deterministic equivalent. What I showed you here for two-stage can be extended to multi-stage. And if the original problem is linear, one obtains a linear programming problem. Suppose today one can solve linear programming with huge amount of millions of variables. One solves that and that's it. Let's start trying to think about it. But you see, even in two-stage case, if we look at that from this point of view of deterministic equivalent, we very quickly run against the wall of exponential growth of number of scenarios. Okay? Now, the revolution that happened again, it's my opinion, not maybe everybody will, is that development of randomization methods. Theory, algorithms, and understanding what problems are difficult, what is not, in, say, at least in stochastic programming, I would say 15, 20 years. Now, the first obvious thing to do, and it's to use Monte Carlo randomization technique. Today it's called SA method. This was coined in our paper actually about 17 years ago, but the idea itself almost as old as the Monte Carlo simulation. So if I can generate, you can think about this function is a value of first and second stage. So we assume here that we can compute this for given X decision first and realization of random down, we can compute this value reasonably efficiently. Maybe it's gradients or subgradients. And this is a problem that we want to solve. In other words, we view that in some sense static problem. So in other words, this can be computed very efficiently. So it's very natural way to do. One generate random sample of that if one can. Right? For that, sometimes I even don't need to know the real distribution. All I need to know how to generate random sample by Monte Carlo techniques, and we replace the true value of that by sample average. Okay. So in statistics, things like that are going back when one replaced the true expected value by sample average to maybe 100 years to development of maximum likelihood. But the emphasis here is very different. In statistics, one usually have a data, which is given by us to something. And one look this problem, for given data. Here, the theory of that, what we'll talk about, that's somewhat similar. But the emphasis is very different because here we assume that we can generate as many realization of that as we wish. Only this, we bound it only by computer times, by a budget, and so on. And we try to solve this problem by law of large numbers. As we go to and the sample size become larger and larger, it will converge to that same probability 1 or things like that. Okay? So again, this is a very simple idea. So instead of solving this problem, which we cannot, we solve that problem for the sample size that we generate. Then it became very popular because it's very easy to implement. One generate sample and then use its software that's one likes. For solve that, it can be, one can use for continuous, for mixed integer. It's not an algorithm, it's just a way of solving that. Let's try to see what it is about. Okay. Now, the question is how large the sample size we need to generate, to solve this problem, I will call it true problem, by this approximation. And any Monte Carlo type, any randomization techniques cannot solve this type of problem with high accuracy. It's inherited in the method. And in fact, trying to solve this stochastic type of problems with high accuracy is misleading because the modeling inaccuracies, engineering all can be much larger than trying to solve, let's say, is a linear problem with precision 10 to the minus 5, 10 to the minus 6. It's meaningless. So turns out, and it was observed as observed in application in many cases, not always, of course, always limitations of that. One can, by solving this type of problem, one can solve the problem with reasonable accuracy, which is enough for applications. So it's possible to give bounds for that, which give us guarantees. Guarantees are always cost something. So this type of bounds that I will talk about that coming from large deviation type theory are not computationally useful. They are far too conservative for real computations. One does something else. But nevertheless, they give us idea of this of what is called sample complexity. How large the sample we need to generate in order to solve that. And this is one of the first results in that area of that type. This is I simplified. It's possible to give it more general. But it involves certain parameters. Here it's a parameter of Lipschitz constant, the diameter. What is most important here is this epsilon. This is what we try to solve, this accuracy epsilon of the first stage. And we solve the problem, this we generate with precision data. You can take delta equals 0. And this is because it's probabilistic, this is probabilistic, this guarantees. So you see this, the sample size grow more or less proportionally to 1 over epsilon square. And this is logarithm, and also n here. N is a dimension of the x, which is important. And I'll come back to that. Okay, so, and this precision epsilon square is inherited in that. You cannot do much better than that, in principle. Okay, this is there's some other algorithms which we have developed. It's possible to talk a lot about that, but I really want to go now to multi-stage case, which is very different. Because I don't have enough time, I will spend some time on that. Now let's go to multi-stage. When so far we talked about two-stage, which in some sense can be considered as a static problem, because for any realization of random vector and then x, especially if it is linear, I can reasonably efficiently compute the values, subgradients, and so on. Now, similar bound can be obtained for multi-stage when we have t-stage problem, finite horizon. And generally, the total number of scenarios start to grow also exponentially with number of stages. So from this point, and this one can get this type of bounds. This is so you see this. It start to grow exponentially with also this epsilon precision of the first stage solution. So in other words, if by development of randomization algorithm was possible to solve two-stage problem with reasonable accuracy, and there's a lot of numerical evidence of that, and of course there are limitations to everything. Multi-stage, when we start to go to more than two-stage, even 3, 4, 5 stages, is different. From scenarios point of view, this determining equivalent was not that much different if we generate, say, number of scenarios that we can solve. But here there's a different principle. There's a very strong theoretical reasons to, I won't say believe, but point that generically, even linear multi-stage stochastic problems are computationally intractable. Even from the point of view of this randomization, if we try to solve that, if we try to solve it, it is not with high accuracy. They have strong reasons to believe for that. And the reason for that is that when I try to approximate the stochastic process, I have to generate the number of scenarios that I need to approximate at every stage, grow also exponentially with number of stages. So then one can say, okay, this is the end of the story, but it's too important to be dismissed like that. So I'll talk about that. I'll start to talk about that. This is negative result. Some positive results that we know at this point. Now, the classical alternative to scenarios is a dynamic programming approach. Also going a long way back, I don't know how many, it's more than 60 years. We can write a dynamical equation here going backward in time. You see, this is what is important here. This is purposely, I formulated this feasibility constraint that way. They only depend on the previous decision and current realization, and also cost functions are like that. So going backward in time, we can write dynamical equations. This is equal to value of cost to go functions, and at every time and period they summarize what will happen in the future. In many books you can see on stochastic programming, you see what is called scenario 3. The first node is deterministic, that's what we go next, and so on. So what is written in our decision at every period of time are conditional. This is very, very important. This is a principle of that. are conditional what we observed so far. Remember, this is notation for the history up to the time t. So, so if I write it like that, at the first stage we're supposed to solve this problem. This cost to go functions, what they depend on our previous decision and realization of the process up to the time t. One of the main difficulties in applying this approach is how can I represent this in a computer? I have to keep track. We have to remember this. If we look at this in general, for all possible realization of that, if we make discretization or something like that, there are too many parameters. It's useless. We have to make some simplification to make it manageable. Okay? And one obvious thing to do is assume that our process, random process, independent from one stage to another. It has different names. We call it stage-wise independence. In other words, remember, it's random vector. Its components can be correlated, can be dependent of each other, but we assume this random vector depends on previous history. In the application of stochastic problem, it's not very often it's not very natural assumption. So I'll say something about that. But if we make this assumption, what happens is that if we look at the last stage, this conditional expectation that I have to write, remember, this is this conditional on that. What happened? Okay, how can I go back now?
You can click left.
Yes. There's no, okay, I managed that. Okay. So if you look at that, this is independent, so it's basically unconditional expectation. The expect value is taken there with respect to that. And if you go back in time, it's say by induction we can prove this, that our value function depend only on this and that, and then even take expectation, the expect value function, and only function of our decision xt. It's possible to talk about state variables here. I will not do that. It's sometimes one can explicitly separate decision variable in state and the control variables and try. But what is important here is what I have to remember that every time at every period of time. And the optimal policy is given by that. So if I somehow I can compute and keep in a computer this value function or cost to go functions, it defines the optimal policy. Okay? The question is how to do that. There are several difficulties to applying dynamical programming. One is one difficulty, we have to compute expected value. Remember, even in two-stage, we have to compute expected value. This is multivariate integral dependent on this on dimension of this random vector here. And it's well known, and in general, to compute multivariate integral for the higher dimensions is not possible in high precisions. So how we deal with it here? We do sampling. We generate a sample of a marginal distribution of that because we assume independence. We only have to look at the marginal distribution, and we approximate it. And there's also this whole theory that I showed you before. We also need to solve optimization problem. This is at every stage we have to solve. In a linear case, and remember the main difficulty of solving that we don't have this explicitly. We have this, what is also called a curse of dimensionality. Even in linear case, this is a cost to go function, this expected value function, depend on that. And when we start this dimension of that start to grow, it's very difficult to deal with that. We have to somehow to keep it in a computer memory because we go backward in time. So one possible way to make discretization of the state space. We make discretization of that. representing that as a finite vector of dimension, not how many we discretize the state space, not the continuous variables, the state space. Now, it has the same problem of exponential growth. So if it is one-dimensional, I probably can discretize. I take 1,000 points, one-dimensional, it will give me accurate representation of this function, I can solve it. But as dimensions start to grow, so maybe for 2 dimensions, I can deal with that somehow. But as let's say 3 or more, it's impossible. It starts to grow also exponentially. In my understanding that it is in the control MDP, they try to solve that when the state space is finite. But here it's essential that the state space, the variables are continuous variables, especially if we look at the linear program. So this approach of discretization doesn't work, of this state space doesn't work for even dimension, say, 4, 5 already. For dimension 10, one can forget about that. Now, so how to deal with it? Of all these computational problems that I mentioned, there's several ways possible. Okay. One way, and I don't have time to talk about other approaches, like using this, trying to reduce the problem by making parameterization of the decision rules and so on. Maybe I'll say like a few words. One way is to try to use approximate. We try to approximate the cost of go function somehow in computationally manageable way. The main point here is that convexity. When we talk about continuous variables, not combinatorial problem, not integer or continuous variable, convexity is the most important thing in a modern optimization. So what happens is, it's not difficult to prove, that if our cost functions are convex with respect to decision variable, in particular linear, if the problem is linear, our cost to go functions, value functions, are convex functions. And this is already somewhat different from typical literature on MDP and optimal control and things like that. Right? We will use convexity. And this is key to what I will say next. Right? If it is convex, it's very natural to try to approximate it by so-called cutting planes. If I can compute the subgradient somehow, that I can try to approximate it by cutting planes. It's also going a long way back in a convex optimization, maybe 60 years ago, famous first paper of Kelly algorithm, things like that. So this is what I will try to do here. Now, what I will say next, again, I don't have time to go into too much of the details of it. So I already start to get short of time. This is a certain type of cutting plane algorithms which proved to be very, I'll say, quite efficient in some cases. It's going back to this origins of that can be traced to this first, probably the first paper of that we see when it is already 60 years ago. In stochastic programming, this was this idea for finite number of scenarios, not too large number of scenarios, is probably was used by Birch. And now it's this SDDP method is attributed to this paper. When it was, you see this also, it already was published on almost 30 years ago, and that time it was nobody paid much attention to that. Today, it's one of the most used methods in that type of trying to solve this problem. So idea is the following. What we, first of all, one is stage-wise independence. What I'll say now, stage-wise independence. It's also possible to extend this method when one has Markovian structure. I probably will not have much time to talk about that, as it's possible to do at a certain cost. Right? And we try to approximate this cost to go function by cutting planes. So it's, the idea is going forward and backward. At every time, at every period of, at every stage right? We have a low approximation of that by cutting planes, which we generated so far. We compute this, this is approximation. We compute the subgradient of that. And this is going to compute subgradient. One has to solve the dual problem. This is linear problem because this is given by maximum of affine function. It's possible to write as linear programming. The size of this linear programming is also proportional to how many cuts we have here, how many supporting planes we have, and then add one more cut to that, going backward in time, and then one go forward in time, one by constructing that. The moment we constructed this approximation of the true cost-to-go function, it generates certain type of policy, feasible policy, because we can go forward in time. So one, in classical application, one generate random sample path, solve that, and that produce point estimate of the value of the approximation of the policy and the trial points. So the idea of this method is that if we look at this original things like that, okay, in order to approximate the function, this is a convex function. Its dimension depends on how many variables I have here. We need, at least theoretically, to approximate it uniformly on a certain, say, finite region which we have here. To approximate uniformly a convex function, the number of these cutting planes, these support planes, also grow exponentially. So generically, also this as a dimension of that grows, and there's no hope of that. But it turns out that in many applications, one does not really need to approximate it everywhere, because we need to approximate where we really, when we generate the policies, where it happens most of the time. And this is probably why it works in some cases. Let me say, nobody solved the cursive dimensionality. If somebody claims that, I have doubts, let's put it this way. But it turns out that in some cases, when it worked out, especially when the dimension of that is not too large, it's possible to solve. What I mean not too large, from a discretization point of view of state space, its probably limit is probably 2 dimension 2. Some cases it's possible to solve 10, 20 variables, depending on the problem. Okay. So, know this by construction. This method became very popular, especially in the power generation. If I'll have time, I'll give you an example of that. This gives a low approximation of that. This the way it's how it's constructed. And remember again, important point. Every time I have these approximations, it generates me policy, feasible policy, or decision rules for discretized problem. Discretized, I generate random sample for marginal distributions. The total number of scenarios still grow exponentially, and also for the true problem. And it's okay, maybe I'll say something like about that. It's possible to show that on average, if I solve SA problem, it gives me low bound also to the true value. This is what I said just a moment ago. It's also defined a policy for the true problem. Now, in the beginning, I said something that why we optimize this on average. What is the real justification of this, trying to optimize this on average? One possible justification of law of large numbers. If we repeat itself more or less under the same conditions, and then we have random variable, if we average, it's supposed to, we average our random data, it's supposed to converge to its expected value. In the way I wrote it before, we average, it's already also by number of stages in some sense. I'll make comment on that before. But recently was a lot of discussion how also to control the risk, because a particular realization of the can be very different from the average. When we control the risk, especially in multi-stage, we typically try to control the risk at every stage. I'll talk about it later. I don't have much time to talk about all of it. Okay, so there's now this very popular general theory of risk, what is called risk measures. One is the most popular risk measure is, it has many names. It's called average value at risk, it's called CVAR, and in different forms, it was discovered and rediscovered by many people. I think I heard that the first time it was discovered about 100 years ago by economists in that form, because these are quantile of this is my random variable. This is basically quantile of that. This is cumulative distribution function. This is quantile. It's average of that higher quantiles of that. So he considered, I think, this distribution of wealth in the United States. So there are many ways, there are many equivalent forms, and it turns out to be the most basic of all of that. It all has dual form. Right? One possible way of dealing with that, we replace the expected value by risk function. Some type of, if I take the expected value here, we will be back to what is we usually call today risk neutral formulation. Now, remember this, our decisions are made conditional what we observe far. This is the sense of the multi-stage optimization. We observe the data and we make the decision. So when we take expected value, if this is expected, we take this functional, which is assigned to random variable, assigned real number. It has this decomposition property. This has also many names. So I take conditional, it will be expected value. When we talk about this type of risk measures, they don't have, it's a theory, in fact, in some sense, they don't have this type of decomposition problem. This class of this, if you know coherent risk measures, the only two has this property, expected value and the maximum. Maximum correspond to robust optimization. With the CVAR or average value at risk doesn't have this property. So when we optimize that, this functional that we look should be written in a nested form. If I take this here, each one of them, say average value at risk, it has conditional analog, can be defined. This nested formulation is not the same as average value at risk, and there are a lot of discussion about that, what it means, what the intuitive meaning of that. I don't have time to talk about that, but it's another possibility. So it's possible to extend this algorithm that we had before, this type of algorithm with not much more difficulty to also the case when we consider the risk measures. And the idea of that trying to control the high quantiles of that. It's a certain type of penalty that we put on large deviations of particular realization from the average. If we minimize, we don't want to go much bigger than that, right? By a design, it's one-sided. Okay. Now, as I already said, to solve multi-stage problem is very difficult, even from this using this randomization sampling techniques. This is in a sense very different from two-stage. What happened in many applications, the process has a certain type of periodical behavior. The example that I showed that was natural. We tried to solve this power generation and on monthly basis, and the randomness was in influence how much is coming in every month, and how we can predict the future. And you can maybe forecast for 1 year, who knows what will happen year after that, and so on. So typically, this is what the people do, they repeat itself, at least from stochastic point of view. From modeling point of view, the one tried to model it in a certain periodical way. It turns out Now, in that case, it's possible to make drastic reduction of the number of stages. One of the problems of this, using T-stage problem of this of finite horizon, is that if I take a horizon is not too large number of stages, then typically this type of algorithms at the end of the time period say, use all your resources, use all the water to produce the electricity, because it doesn't care what happens after that. It's called end of horizon effects. Because of that, in some applications, people extended that to many other stages to take care of that. So one possible way of dealing with that is the following. So I'll have a few probably moments to describe that. I still have a few minutes. First of all, we take this infinite horizon and we take this, we use discount factor. Why we do that? No, some of people just try by economical, but my guess it's just to make this problem possible to mathematically formulate that. So if our values are bounded, it's basically geometric series, it will converge. At least it's the series converge. We can talk about that in mathematical sense. And then I will talk about this, say, linear constraints. It's sufficiently general, and there's a probably already also that type of state constraints here. Let us suppose that statistically, stochastically, the process repeats itself with period m. The distribution is the same. Random process, it's random still. The process is random, but the distribution repeats itself every, say, 12 months. And the cost, all the parameters repeat the same every, say, 12 months. It can be m, and can be equal even 1. In that case, we can write what is called Bellman equations, which is a very standard in a MDP, in optimal control, taking into account this periodical behavior of that, and I wrote it here. Right. So if m equal to 1, let me see this. In that case, we reduce the multistage to static problem. Here it will look at that way, because it's all we look at the linear case. No, typically it also will be linear. This is our discount factor. And if this is risk neutral, we take expected value. In more general, I can take some risk measure. Okay. In a periodical case, it is also possible to write it. It's analog. So we reduce the problem trying to solve instead of many, many stages. You can think about this approximation with large T here. And it's possible to estimate the tail of that by its geometric, because of geometric series. Okay? We reduce it to much smaller number of stages, trying to solve that by using basically the same cutting type methods. And I'll show you numerical results in a moment. It's possible to show that this is a more or less classical. It's adjusted here to the problem that we considered. This is called Bellman operator. It's possible to prove under various general conditions that this is a contraction mapping. Because of that, the equation that I showed you before have solution. The solution is unique. This is a classical thing. So we tried, and it's also interesting to see, in this point of view, statistical properties of that. What it means, statistical properties of that, right? Remember, we replace the true distribution, we discretized it, say, by Monte Carlo at every stage, assuming stage-wise independence. So we replace the true distribution by what is called empirical distribution. So it's not difficult to show. Here I wrote it for risk neutral case. It's also possible to write for risk measures. We have this bar, simple bar. Okay. What is interesting here, how it's all behavior of that depends when this discount factor gamma start to get close to 1. In the application that we considered was very close to 1 for various reasons. I'll show you it in a moment. So usually the value of that, the value of the solution that you have is more or less proportional, and it was observed numerically, to that. More or less proportionally to 1 divided by 1 minus gamma. Okay? So you see this bound here. So in other words, how large the sample size I need to get good approximation, especially when this start to approach 1. It's not completely clear. This is related to sample complexity of that. Maybe I'll say a few words about that later. All right. What is interesting here in the classical SDDP, if one knows about that, by generated random sample, one also construct point estimate of the value of the current value of the approximation of the strategy of the policy. And then one can construct statistical upper bound for the value, and then one can has a gap between low bound, which is deterministic by cutting plane, and upper bound, which is given by in statistical sense. And amazingly, in some cases, very large problem, one can solve problems with this type of proved accuracy, 5% of accuracy, relative accuracy. No, you say 5%, it's very bad. But imagine the problem, unimaginably large problem, which is simply inaccessible by deterministic type of methods. Right? So when they start to get close to 1, doesn't work for this particular case, because we need to take we approximate the infinite horizon by cutting it some. And if I want to estimate the tail, it's geometric series, it's easy to estimate, but it depends also how close that to 1. It doesn't work for that when it's, say, when it is, this value is 0.99. So it will be 100. It doesn't work. So what is interesting is it's possible also to write dual of this problem. Remember this, if we look at this linear programming problem here, okay, if we look at this linear programming here, all right, it is when we have finite number of scenarios, you can in principle, can think about a deterministic equivalent of that. Deterministic equivalent of that is a linear programming problem with astronomically large number of variables and constraints. But it's linear programming problem. So one can think about the dual of that by classical theory of linear programming. Value of dual of that is the same if they have finite value. So one can discretize these constraints. Right. So and then write this a dynamic programming equation for the dual, and then give the upper bound, which also can be, one can also apply this. I wrote this equations corresponding. It's possible to do. There are some problems of that, but it worked reasonably well for that, and this gives deterministic upper bound for the value of the problem. I'll show you in a moment. I'll show you examples. I have just a few minutes. Let me show numerical examples. There's by the way, if somebody interested in that, please send the email. I will send you links and papers and all that. It's possible also to write this dynamic problem equation in for dual problem and also for periodical one. Okay, it's all possible to do. This became classical examples. We worked on this project about 10 years ago. All right. Maybe a few words about it if you don't see it before. This is a 120 stages when originally we had 4 areas, and the question was how to use the water to generate power. It's a very typical example of that. And it's here decision made on monthly basis. So the planning was for 5 years. And then another 5 years were used for end of horizon effect, to deal with end of horizon effect. at the end was 120 stages, because also the inflows, which is supposed to be random, were considered as first order regressive process, gave good periodical, because there are seasons, the rainy seasons and dry seasons on a monthly basis. The first order, at the end, it was possible to formulate as basically with 8 state variables. So that you see 8. Okay. No, this is how it's. So recently we tried to solve that using periodical, which periodical take automatic care of end of horizon effect. The natural period was 12. It's also up to us how to choose this period. And it showed out that, first of all, it was possible to drastically reduce computational time on that. And the solution was, especially at the first stages, was very similar if we solve that with this 120 stages. It's automatically take care of end of horizon effect because it's cyclical, it's periodical, go back all the time. And it was very important what discount factor to use. This is a reasonably small discount factor. In real applications, they use this discount factor. Why? Because it was considered to be 12% on a yearly basis. You see, it's very, very close to 1. In fact, this is what I talk now. They even say that even they want to reduce this one, which will make it very, very close to 1. And it's well known in all that when this discount factor starts to approach 1 more and more, one has problems, computational problems, all that. It's understandable. But even with this type of that, the first, the end of horizon was different, because if we use all 120 stages, finite horizon, algorithm at the end, say use all the water, it doesn't care what happens afterwards. Here it was much more periodical. First few stages were very similar in that case. Now it's also possible to construct the dual bounds of that, solving dual problem. Remember, at the end, we solved that linear programming problem with number of scenarios bigger than number of atoms in our universe. And we tried, and this is let me show you this final result. I have to finish now. I already a few minutes, right? Even with this discount factor that close to 1, and this is 12 stages. Notice in this experiment was used 50 samples discretization per stage. For simplicity, we took 4 stages, assuming independence. This is how it converges. This is lower bound, for that, which is deterministic. This is upper bound, which is also deterministic. How it works, the upper bound works, one take very large number, constant, to make sure that it is bigger than the value of that, and let's start to add cuts. As one add cuts, it becomes more and more difficult to solve, and many of these cuts become redundant. So what is showed empirically to be worthwhile to do from time to time to reduce the upper bound. We know already that is the value of that smaller in certain number, and start from the beginning, removing all the cuts and start there, converge much faster and to reasonable accuracy. So it's still going in a process of trying to understand all of that, especially how this all affected when this discount factor is very, very close to approaches 1. So at this point, I probably should stop. If any they have questions, please. Yes.
Okay, let's thank Professor Shapiro again for the great talk. And maybe let's look at some of the questions raised in the Q&A section. So the first question is regarding the problem of multi-stage stochastic approximation.
Can you please tell me the first name of the person that asked it? Maybe I know. Okay, doesn't matter. Okay, what is the question?
Oh, so the question is whether there are, could you please introduce to us some of the recent progress in terms of the uncertainty quantification for the problem of multi-stage stochastic optimization?
I'm not sure what one means by that, what it means uncertainty quantification.
Oh, I think the question means drawing confidence intervals for the solution obtained by the sample averaging method for multi-stage of stochastic optimization.
No, if we go back into two-stage simple one. Okay. Suppose we generate by Monte Carlo method. So, and this is equal to this how many scenarios you generate 1 over k. It's possible to give the asymptotic distribution for the value of this problem. It's an old result, which in some cases it has asymptotically normal distribution. So in principle, one can try to write confidence intervals. They are not useful. It's nice theoretical result, which give us some ideas about this. Why they are not useful? Because typically, even when we talk about two-stage, it's biased, downside bias, and the bias often has more or less the same magnitude as variability coming from standard deviation. So there have been attempts to construct a confidence interval. They are not really useful for practical applications. It's more theoretical things about that. So there's a the standard technique of that is that when we compute the value of this for the sample average approximation, it on average it give low bound, and this can be statistically estimated, and then one use a point and a certain point, and that give you upper bound. And this give you accuracy of the solution in estimate of this accuracy of your solution in two-stage case. Similar thing can be done in multi-stage case from statistical point of view. I think I mentioned it here. Okay, where is that? So in other words, the construction, this type of classical confidence interval is not useful in my opinion. It doesn't work in numerical. Oh, here. So the idea is the same. This is a value of the sample after we make discretization. It's statistic. It's stochastic. It depends on the sample. So on average, it's smaller than the true value. So if I make some point estimate of that, I can estimate that by usual averaging and get lower bound. And the upper bound I can estimate by the value of the function or by constructing the dual. And that gives reasonable estimate of the gap, optimality gap, how we solve that for the true problem. True problem, by true problem, I mean the problem with continuous distributions. So if somebody interested, it was recently posted online Python software for that with the description, all of that in numerical examples, and one can use it. It works reasonably well and give a bound almost for discretized problem and for true problem statistically. I don't know if it answers the question. Is it?
Yes. Thank you so much. Mm-hmm. And the second question is regarding the stochastic dynamic programming problem. So here it seems that you have a function qt and you construct a piecewise linear function which is a lower bound of this qt. I was wondering whether you ensure that somehow ensure that the qt functions are all convex.
Okay, let's see. Okay, this is you talk about this one for me.
Yes, the qt which is on the left hand side of this equation.
This one. Oh, yes. If the problem is convex, in other words, this, no, say it's linear. If the problem is linear, these are convex functions. This is a theory. It's not difficult to prove. In fact, even if the cost functions, where is that? If the cost functions are convex with respect to xt, and here the constraints are linear, the value functions are convex. So it's guaranteed here. And the law of this one is simply constructed as a maximum of affine functions. So it's piecewise linear convex function. So this is a different, essentially different from formulations, say, or in optimal control, where this convexity is not that natural.
Okay, thank you. And another question is regarding on the notion of stage-wise independence. I think it appears from time to time. I was wondering whether you could elaborate more on this, on the definition of this stage-wise independence.
Stage-wise independence, well, okay. Stage-wise independence means that we have a random process. Okay, here we view the data as stochastic process with all the theory about it. Right? If we have finite number of stages, we can look at them all together, and supposedly they have it's a large dimensional random vector, all them together. It has distribution, some probability distribution from theoretical point of view. This is not very useful because what we observe there, we look at that with respect to the time t. So in order for that to have useful, because if I don't assume anything about my random process, when I start to write dynamical equation, I have to remember everything. From statistical, as a statistician, when we model random process, it's always Markovian. Markovian, I don't have to remember everything what was in the past. It's impossible. And in fact, it's usually not the case. I have probably to remember last realization, last few realizations. The simplest possible case is that when we have what is called stage-wise independence. This is random vector, and this is a history of the process up to the time. It's also random vector. They independent of each other from stochastic point of view. If we assume that, this is all simplified dramatically. Now, in many applications, at least in this, for example, in optimal control, this is usually considered as a noise. If you know the formulation of optimal control, it's usually considered as a noise. And there it's very natural assumption of independence. Noise is assumed to be independent from one period of time to another. In application of that, it's not usually noise, it's data process. So assumption of independence is not natural. In fact, in many cases, it's a demand process, or this example that I showed that it typically was possible to model as a statistician as autoregressive type of autoregressive process. But nevertheless, it's Markovian. So the simplest possible case, independent. If this independent, then by going backward time, by induction, it's possible to show the cost of go functions do not depend on the history of the process. It makes enormous simplification of it, right? So if this is not independent, which is often the case in applications, if we, for example, we have autoregressive process, linear autoregressive process, sometimes it's possible to formulate in terms of the error, if you know what regressive process is, and by artificially adding state variables. It's a standard treatment, which increases the number of state variables, and this is a cost of that. But nevertheless, it's possible, and this is what we did in the example that I showed you. Another way of doing that is that we have Markovian structure to approximate it by finite Markov chain. That has its own limitation, and it's still not completely, I will say. There are very few numerical examples that were available, real numerical examples, not some simple toy examples. And theory of that is still, there's a lot of things which are not completely clear. But this is how, so far, we deal with that. And this is an example that I showed here. Originally, it was the number of state variables was 4 because the regions was aggregated in 4 regions, and it was because the process was modeled as periodical first-order regression process. At the end was 8 state variables. This is this state of the art at the moment. I don't know if that answer your question.
Thank you. So it seems that we are running out of time. Maybe let's ask the last 2 questions. Maybe the first question is regarding the risk-sensitive part, the infinite horizon dynamic programming with nonlinear functional R. And so for this problem, it seems that you have a bound on the solution obtained by sample averaging and the population solution. I was wondering whether we can have a uniform bound over where we take uniform convergence over the psi function.
Okay. When we have this risk neutral, this is the expected value, we have possible to construct upper bound in 2 ways. One way is stochastic, okay? Because then it's possible to do the sampling and all that, and it's also work in the periodical case. The other is a constructing the dual problem that I showed you. We don't know how to do that for general risk measures, and my guess it's not possible. So for general risk measures, we don't know how to construct the upper bound. It was some suggestions made, but they work only for low dimensional that by making basically discretization of the state space. We don't know how to do that. Unfortunately, this is a state of moment.
Oh, sorry, I was wondering whether we can bound the Q hat and the difference between Q hat and Q, which seems to be in the following slides.
I'm talking about numerical thing. Okay, when we look at this, when we try this to problem this solve, this here, for example. Okay.
Oh, yes. Here the difference between this Q and the Q hat N seems to depend on the psi function, where psi is defined also depending on Q.
Okay.
So I was wondering if it's possible to take a uniform convergence over the function class in some sense.
Yes and no. When we, first of all, the examples that I show you, it's after discretization. This gap here is numerical. So in principle, if this converge and we can can do it indefinite time, it will converge to 0. This because it's numerical gap. It's numerical. It's coming. We solve the same problem here and this here. We find a number of scenarios. Okay? So there's a gap simply because we cannot solve that to high accuracy because problem is huge. Now, there's also statistical gap. This is exactly what we're talking here about. Okay? Because of approximation. How large the sample size we need to use. This part here is possible to estimate the same way that I did before. Okay?
Mm-hmm.
And that suggests if I do this that way, it's still not clear. It suggests that the error of stochastic error, this is different. It's coming from the error because the sample just approximated by the sample of order 1 divided 1 minus gamma in the power of 3. Why? Because you see, this is 1 appears here, and this is also more or less proportional to this 1 divided by 1 minus gamma. This is true value of that. Now, if we look at the relative error, which is more natural, it will, this bound give this part of that. It's not clear what it really happens. It's a bound. Okay. Maybe it's much smaller than that. Some numerical experiments, and it's just early stages of what we do. Seems that it's much better than that because when it's think about that, this is a discount factor of 0.99. So it's 100, and it's quickly increased. It seems to be this gap between, and this is uniform gap that is written, it's uniform norm. Here, it's usually seems to be, doesn't depend that much when this approach is one. And this is most interesting case. So it's not clear.
Mm-hmm.
And there's a difference here. So yes, you can approximate that. This is all known, okay? These are available, this you can approximate that. That give you bound for that, but this bound is what appears here is this. So
Mm-hmm.
it's not clear, completely clear. So, and relative error is more or less proportions. It suggests relative error of that, of all this approximation. Okay. Is more or less proportional to that. But it seems to be better than that. Again, we don't know. It's very recent results. And we don't. Mm-hmm. So it's a very interesting question. How all of this happens when this approach is one? Mm-hmm. When it's become not 0.99, but 0.999, which is in application happens quite often. Mm-hmm. This it starts to become bigger and bigger and bigger.
Okay, thank you so much. And the last question is regarding the numerical result. In your last slide, it seems that the green curve has multiple descent, has a multiple descent phenomenon, and I was wondering why this happens in the numerical experiment.
This line is one how this computed. One take very large upper bound to start with to make sure that it is larger than the optimal value, and that at cuts and cuts and cuts, you see it doesn't converge well. Mm-hmm. For this discount factor very close to 1. So here, what happened, what done here, it was the upper bound was reduced because we already know, and it started all new. All the degenerate cuts were removed, and it immediately see its improvement. Then it was again made, the same type of trick was again made here. This current bound, and there's all cuts removed and start from new, and you can see it much faster. Here it was done, I think, every 100 iterations until here. It's even worked even better. So every 100 iterations, we know what is the upper bound, and the algorithm starts from the scratch.
Mm-hmm. Okay, thank you so much. And I think we are running out of time, and also let's thank Professor Shapiro again for the very nice talk, and also thanks everyone for joining. And we are looking forward to seeing you guys next week.
Yeah.